recall that we had defined the set of rational numbers Q to be the collection of all elements of the form m by n such that m comma n come from the integers and n is not 0. Now there is a problem with this definition. From our axioms of set theory, we require that every element is itself a set. But it is not clear what the meaning of m by n is. What does this even mean? It's not really a set, it's just a formal set of symbols, m with a bar and then n at the bottom. It's not really clear what it is. Now, one way to fix this is to view m by n as the ordered pair m comma n. We can just introduce another notation that m by n in actuality means just m comma n. In the module on relations, we have already seen that ordered pairs can be represented as sets. There is no problem here. Now, this new definition still has problem. We can still view rational numbers like this, but the element which is 2 comma 4 and the element which is 1 comma 2 correspond to 2 by 4 and 1 by 2, which we all know from elementary mathematics, they are both the same. So many elements in this collection of rational numbers defined as ordered pairs m comma n from integers where n is not 0, many elements themselves are equal. So it is nice if you could somehow redefine what equality means in a set. And the notion of equivalence relation does this precisely. It is designed and to actually make precise such things. So definition. Let A be a set. Let A be a set. An equivalence relation we will usually denote equivalence relation by this tilde. Denoted by tilde is a relation on A that satisfies it should satisfy the following three properties. Number 1, the first property is called reflexivity. This says that every element is related to itself. For all x in A, x is actually related to itself. Okay. Number 2, symmetry. This says that for all xy in A, x related to y implies y related to x. Okay. And the third property is that transitivity. Transitivity says that for all xy, z in A, x related to y and y related to z implies x related to z. Okay. So this is the notion of an equivalence relation. It is a special relation on a set that is reflexive, symmetric and transitive. If you note carefully, what we have essentially done is we have taken the characteristic property of equality and formulated it as these three properties. Remember, equality is supposed to be logical identity in our framework. An element is obviously logically identical to itself. If A is identical to B, then B is identical to A. So symmetry is also something that's shared by equality and equivalence relations. Same thing with transitivity. We have captured the three essential properties of equality and framed it as an equivalence relation. Let's see some examples. Well, the first one is the rational numbers. On the collection of ordered pairs, m comma n in z, n not equal to 0. This is what we call Q. On this, define an equivalence relation that says that M comma N is related to P comma Q if and only if MP is equal to NQ. Okay. Now, the fact that this is an equivalence relation, is just elementary arithmetic, which I leave it to you. There is really nothing to check. That this is an equivalence relation follows from elementary arithmetic. From elementary arithmetic. So, the set Q of rational numbers is in fact not just a collection of ordered pairs. There is an additional equivalence relation involved, which we will make precise just in a moment when we come to partitions. Okay. Now, another example. Fix n in the natural numbers and on the integers put an equivalence relation A is related to B if and only if n divides B minus A. Again, that this is an equivalence relation, follows from elementary arithmetic. That this is an equivalence relation follows from basic arithmetic. Fine. So, this equivalence relation will give to something called integers modulo n. Okay. These are very important in cryptography and number theory. Okay. So, let me give another example of equivalence relation. On the integers, put an equivalence relation, not an equivalence, put a relation, sorry about that. I will give a non-example now. On the integers, put a relation that A is related to B if and only if A is less than or equal to B. Okay. We have put a relation R on the integers where A is related to B if and only if A is less than or equal to B. Now, this is clearly symmetric. This is clearly reflexive because A is less than or equal to A, but it is not symmetric. Okay, if A is less than B, that means A is less than or equal to B also, then B cannot be less than or equal to A. This is not true. Okay, so this is not a symmetric relation, but it is transitive. If A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C. It's certainly transitive. Okay, so we have given 3 examples. 2 of them are about positive examples and one is a counter example of an example of a relation that is not having all the properties of an equivalence relation. Now let me give just one more example, which is going to be a real world example. Just for this example alone, I will violate our solemn oath that we will only consider sets whose elements are themselves also sets. We will violate that and I will give you a real world example. Okay. Now let P be the collection of all people. P be the collection of all people. Define a relation that person A is related to person B if and only if B is a friend of A. Okay. Now we can make some interesting remarks about this real world relation. Please don't take this example seriously. I just want to illustrate the mathematics with a bit of off the cuff humor. This relation is actually not reflexive. Why is it not reflexive? Because we know that sometimes you are your own worst enemy. your own worst enemy. Okay, so this is not reflexive. Even more sad, this is not symmetric. This is not symmetric. If you think about it, why? You can consider some other person as a really good friend, but that person may not share the same feelings. Certainly, this is not transitive. This is not transitive. Okay. So, this is just a real world example. Please don't take it seriously. It's just to illustrate the concept. Let me give you an exercise for you to solve. Exercise. Again, consider the collection of people P. Collection of people P. And put a relation R where person A is related to person B if and only if A and B share a biological mother or father. Okay. Now, there is no necessity that you have to have the same father and mother. Step siblings are also considered. So, this is the sibling relation. Sibling relation. Now, check which is this relation symmetric, reflexive, or transitive. Which properties does this relation have? Please solve this exercise. Okay. Now, given an equivalence relation, I said that you can redefine equality on the set. Now, I'm going to make that precise by defining what is called an equivalence class. Equivalence class. Okay. So, we have set A and an equivalence relation. Equivalence relation. Tilde on A. Okay. Let S be an element of this set A. We define the equivalence class S, the equivalence class of S under tilde is the set which is denoted by square bracket S. This is just defined to be all the elements X in A such that X is related to this given element S. So, given an equivalence relation on a set, take an element and collect together all those elements that are related to this given element. That is called the equivalence class under this equivalence relation. We also have an associated notion of a partition. So let me just define a partition. A partition P of a set S is a subset of power set of S. Recall the power set of S is the collection of all subsets of S such that first point, the union of all the elements of P. Remember, each element of P is itself a subset of the original set S. So it makes sense to take the union of this collection. This is going to be the whole of S. 2, if A1 comma A2 is coming from P and A1 intersect A2 is non-empty, then A1 is equal to A2. So a partition of a set is nothing but breaking up the set into a number of pieces such that the pieces together give you back the set and no two pieces intersect. So it's a very intuitive thing. We can draw a picture for the partition. It's suppose you have a set like this, some set. A partition is something that looks like this. Each constituent part is supposed to be one of the elements of the partition. Okay, so now we have the notion of a partition. How is this related to the notion of an equivalence class? Well, we have the following proposition. Given an equivalence relation on a set S and A comma B in S such that the equivalence classes of A and B are disjoint, then not disjoint, sorry, the equivalence classes intersect, then A is equal to B. Note that this is the second property of a partition. If two subsets of P do not intersect, then they have to be identical. So let's see a proof of this. So what we do is we have to show that every element of A is there in B and every element of square A is there in square B and every element of square B is there in square A. So I will just read this. As square A or bracket A. Okay. So suppose C is an element of the equivalence class of A. Then we can find, first of all, we can find some D which is there in the intersection. Okay. Now let's write down what is the meaning of D belongs to A, equivalence class of A intersect equivalence class of B. It just means that D is related to A and D is related to B, because the equivalence class is the collection of all elements that are related to the particular element B or A. Okay. Now C is in A just means that C is related to A. Okay. Now putting these two together with transitivity gives C is related to D. C is related to D. Correct. Now D is related to B and C is related to D means that C is related to B, again by transitivity. Okay. So what does this show? This shows that C is an element of the equivalence class of B. Now the thing is, we must still show, so what does this show? Ultimately what we have shown is that B is a subset of A. The equivalence class of B is a subset of the equivalence class of A. But we have used no property of the equivalence classes of A and B other than the fact that they are disjoint. So by symmetry, A is also a subset of B. Note, when I say by symmetry here, I do not mean symmetry of the equivalence relation. What I mean is the symmetry of the nature of our argument. There is nothing about A or B special when we showed that B is a subset of A. The same argument works for A is a subset of B. By symmetry, A is a subset of B, which means A is equal to B. Okay, so this is promising. What has happened is, if you take two equivalence classes either they are going to be completely disjoint or they are going to be the same. So you should have anticipated the theorem that's about to come up. Theorem let S be a set and tilde an equivalence relation on S. Let P be the collection of all equivalence classes of S under the relation tilde. Then P is a partition of S. Conversely, if P is a partition of S, we can find an equivalence relation tilde whose associated partition is P. So what does this theorem say? It says that if you start with a set that is equipped with an equivalence relation, you consider the collection of all equivalence classes, that gives you a partition of the set. Conversely, you start with a partition of the set. We can define an equivalence relation in such a manner that if you consider the partition generated by that equivalence relation, in other words, the collection of all equivalence classes under this equivalence relation, then you get back the original partition. Okay. So, proof. So, we know that collection of equivalence classes satisfies property 2 in the definition of equivalence relation of partition. That is, we just showed that in the previous proposition that if two equivalence classes intersect, then they must be identical, which is exactly what condition 2 in the definition of partition states. So all we have to do is check condition 1. What do we have to check? We have to check that union of P is S. But this is obvious because for all A in S, A is an element of the bracket of A, the equivalence class of A. This just comes from reflexivity. This is just reflexivity. Okay. So both properties of partition are satisfied by the collection of equivalence classes. Now let's start with the partition P. Let P be a partition. We have to show the converse and construct an equivalence relation such that the partition of equivalence classes of that equivalence relation gives you back the original partition P. Let P be a partition. Define A related to B if and only if there exists A in P such that A comma B are both elements of A. So what I do is I look at this partition. It will consist of several sets which are subsets of the given set S. I put the relation that A is related to B if and only if there is some element in the partition, in other words some subset which is present in the partition, such that both elements A and B belong to A. Now first, reflexivity is obvious. Why? Because A comma A will belong to A. 2. Symmetry is equally obvious. Symmetry is equally obvious. If A comma B belong to A, then B comma A also belongs to A. Third, transitivity is also equally easy. If A is related to B and B is related to C, that means A comma B must belong to some set A and B comma C must belong to some set B. Okay, both should be elements of P. But A and B are not disjoint, they have the element B in common. So because P is a partition implies A is equal to B. The set A is equal to the set B. That means A comma B comma C belong to A, which means that A is related to C. Okay. So the equivalence relation that you get from the partition is straightforward. You declare two elements to be related if and only if they belong to the same subset. Now for the last part, I have to show now that the partition that is got from the equivalence classes under this relation is same as the original partition. There is really nothing to prove. So I just want you to pause the video and just think about why this is true. So this concludes the module on equivalence relations. Thank you.